Well, welcome everyone. Happy New Year. I hope you and your family are healthy and that you're excited to learn some stacks and moduli theory. So my name is Jarod Alper. I'm faculty at the University of Washington, and this is a course that I've opened up to the larger community on an introduction to stacks and moduli. This is really like the second part of a 3/4 sequence here that we're offering as topics courses at UW, but this course is completely independent. We will, however, use some of the material that Max Lieblich developed last quarter on resolutions of singularities, and in particular, resolutions of surfaces and related stuff. And we need that for, when we address stable reduction for curves later. And that, in turn, will play a crucial ingredient in Johan de Jong's course next quarter on alterations. Although I think he'll probably need a more general result than we'll actually prove. But anyway, so I just want to get started with some course logistics. There's a course website, and I have a course email list, and everything will be posted on the website. The overall goal of this course is to introduce the theory of algebraic spaces and algebraic stacks, but with moduli always in mind, and in particular with the moduli space of curves in mind. So whenever we introduce a new definition or proposition, we'll always sort of try to translate it to say, what does it tell us about the moduli space of curves? And overall, the main goal of this class is to establish this theorem that I have written here, that the moduli space mg bar of stable curves of G to G is a smooth, proper, and irreducible Deligne-Mumford stack of dimension 3G minus 3 with a projective coarse moduli space. So there's a lot of words that we'll need to define here. Namely, we'll need to define what stable curves are. We'll need to define what a Deligne-Mumford stack, what it means for it to be smooth or proper or irreducible, what the dimension means, and what it means to have a coarse moduli space. So we'll introduce these topics in the course of this quarter. And maybe before I say anything else, this is a lot of background material that goes into this theorem. I hope you're not thinking I'm going to give a complete proof of this statement. At sometimes I'll have to give like a high level arguments because it's just too much background material, and some of the results are really require a lot of foundations. And so for some of the logistics on the course, we're on the quarter system here at UW, and so there's around 20 lectures, each around 80 minutes. And what I'm imagining, I don't know if this will work out, this is really an experiment, is that I'll have more like an action-packed 60-minute lecture, and then reserve the final 20 minutes for more questions and discussion. But really, questions are welcome at any time. But yeah, I would hope to save and reserve the longer questions that require more time until the end. And yeah, lectures will be recorded, and I'll post them on YouTube with links from the website. Right now, just to keep things simple, I haven't set up a Discord Azure server, but if there is interest or demand, it might be a convenient way for everyone to interact. And so, yeah, let me know if this would be a good idea. And I'm also writing rather detailed lecture notes to go along with this course that I'll be posting. Right now, I just have a long introduction, which is basically just like some history and motivation for the entire course, which I'll cover some of today, but we'll sort of, after today's lecture, which will be like a broad overview, we're just going to dive into the details next time and of growth-critique topology sites leading to sheaves and stacks. So my notes are posted on the website, but these notes draw from a number of other references, and so I've tried to list some of the key references below here. So there's some wonderful books by there's Lamont Morib-Lee, there's Knudsen and Olsen that provide all the foundations for algebraic spaces and stacks. And then Vistali's has some nice notes on growth-critique topologies, fiber categories, and descent theory. And then And then there's the ultimate reference, which is the stacks project. Which contains most of what I'm going to be doing in this course, often in much greater detail. And so for the background on the moduli of curves, the quintessential paper here is the Dlee-Mumford's original paper, the irreducibility space of curves of genus G, where actually in this paper, it actually is the first paper where it introduces the notion of an algebraic stack. So it could also go in the list of stack references, but this paper is sort of famous, and then it never actually proved any of the statements about the foundations of stacks, but nevertheless used them to prove a really powerful theorem that that MG is irreducible and positive characteristic. And we'll cover a lot of those ideas in this course. There's also the wonderful book by Harris and Morrison on moduli of curves. And I think sort of part of the goal of this course is to introduce the technology and the language of algebraic stacks, so that then when you pick up this book by moduli of curves, which has a lot of high-level arguments about curves, that you can fill in the details yourselves with the language, using the language of stacks. And then we'll follow to maybe the hardest part of this theorem, which I won't be able to prove in complete detail, is the projectivity. And then we'll rely on Kolar's method for projectivity, which we'll get to at the very end of the course. And again, with a lot of the foundations on curves, it's also a lot of it's contained in the stacks project. Any questions about the course logistics?
A small question about questions, like how do you want to receive them? Do you want things in chat? Do you want us to just unmute and talk? Do you want to use the participants thing?
Yeah, thanks. I think I don't think right now I can monitor the chat window, so I would prefer if you unmute yourself and just ask. Yeah. And I know, these lectures are recorded, so I know that there might be some reluctancy to speak up. I'm also reluctant myself to, crack jokes because they're all recorded. But yeah, any other questions?
Do you post the recordings on the website?
I missed that.
Do you post the recordings on the website?
Yeah, I'll post links to the videos on the website. Yes. I'll probably, I may cut certain sections of the video, like maybe the discussion sections or the beginning and the end. But yeah, all the lectures will be recorded. So yeah, okay. So maybe I'll just give some some tips and advice for how to treat this material. First and foremost, learning the theory of moduli and the theory of algebraic stacks is hard. And it requires active learning, requires work. I mean, you can sit back and just listen to these lectures and get a high level picture of what's going on. But if you really want to work in this theory or do research in this theory, you have to dive down into the details at some point. And one of the reasons why it's hard is, so it's similar to when you first learn scheme theory. You have to absorb a number of new subjects and ideas simultaneously. When you learn scheme theory, first you have to stop thinking about varieties as explicitly embedded in a given affine variety or a given projective variety. And you think of them, sort of as a set where you have to allow generic points, not only closed points. And then you endow it with a topology that the first time you see it, this is a risky topology, is a new concept. And then you endow it with a sheaf of rings. And so you need to learn the technicalities of sheaf theory. And at the same time, you allow nilpotents into your function. So schemes are simultaneous. There's a lot of things you need to simultaneously learn. So in a similar way, when you learn the theory of stacks, you need to learn first the functorial approach in the algebraic geometry, which we will say a little bit about later today. And then more generally, you need to start thinking about groupoids. That is not just what the objects are, but what the morphisms and isomorphisms are, and what functors of groupoids, that is what stacks are, which is a machinery that we'll develop. And you can't just work with the Zariski topology. We'll have to replace it with the Ital topology, which isn't a conventional topological space. So that's another abstraction you need to handle. And for that reason, we also need to systematically use descent theory because we're working with the Ital topology. And finally, we need to rely on several advanced results that probably aren't covered in a first course in algebraic geometry, namely advanced properties of like flat and Ital, unramified and smooth morphisms. We'll rely on the the existence, the existence of Hilbert schemes. We'll use some material on like what an algebraic group is and what an action of an algebraic group on a scheme is, and the notion of principal G bundles and torsors will come up. There's some basic deformation theory we'll use, primarily infinitesimal deformation theory, and we'll use Schlesinger's criterion at some point. And then there's this powerful result of art and approximation that we need. And finally, we'll have to use some results in the birational geometry of surfaces. And each of these topics is, I will not develop in complete detail. In my notes, I'm going to have appendices that address these. But at the same time, as like learning the subject is hard, also teaching it is hard. Finding a linear way to present this material is sort of challenging. There's so much to say and not so much time. And at the same time, now there's 155 participants. And from the emails I received from you, there's a lot of different backgrounds. We have undergrad students, primarily mostly graduate students, but there's postdocs, there's faculty, there's people that have left academia but still retain their interest in algebraic geometry. So yes, I hope you bear with me. I mean, this is really an experimental course, and I won't feel offended if you don't show up on Wednesday. So some tips of how you should approach this subject is really you need to work through some of the material yourself. You can't just sit back and listen. And I think what I tell my graduate students is always like examples. No matter if they start with simple examples and then build up the complexity, but work out your own examples. That's how you can understand the theory. Do exercises. I'm going to have a list of exercises in my notes, but there's also exercises in Olson's books. And then there's many details I'm going to leave out of the proofs in the lecture. And also, even in the notes, I'm not going to have all of the details there. In many cases, like I'm going to leave out the details in which it's, details that are better worked out yourself. I mean, often you get a lot more value of figuring it out yourself, and it's actually tougher to follow someone else's argument for some details. And maybe moving on here, here's my advice is do not try to read the notes linearly. And I think as a graduate student, one of the first books I read in my second year was, I read Hartshorne, and I did read it linearly. And because you kind of, when you learn scheme theory, you really need to understand sheaves well before you move further. But with this subject is very different. That you can take a nonlinear approach because there's a lot of different components that are kind of independent, and then you can sort of black box certain results and to try to get an overall understanding. And I think you should just accept right now that there's a lot of topics in this course that you don't know, and you still won't know in 10 weeks. But you should try to take a big picture view and use such machinery anyway. And so that really what I'm trying to say here is that, and this is a lot, this is similar advice I would give to when you go from, learning graduate level math to trying to do research. And you need to find that balance. It's a very delicate balance between, on one hand, accepting and using and having the big picture view of advanced results. And the other hand, of understanding the details for why those results and the proofs and why they hold. And similarly, there's a balance between accepting details and arguments and checking details. And what you might really need is some sort of faith that you could work out the details if you need to, or that maybe there's some theory that you should just have the confidence at some point later on in your mathematical career, you'll invest the necessary energy to properly learn that subject. And so, yeah, this is a delicate balance, and the hope is that eventually you can tip the scale to where you're more into the into this category where you both have the confidence you could work out the details, and then that there's a number that you have. Great. Any any questions? Okay, moving forward. Okay, so today I would like to actually get started and say something here. And like today's lecture will be basically a historical motivation, and I'll try at the end to say some things about the functorial approach in algebraic geometry. To begin with, I want to address, concept of moduli. What is moduli? What is a moduli space? And it's this is a word that shows up in all different branches of mathematics, and it's not easy to formally define. So I'll vaguely define this here, where as follows. So we're going to take, you consider your favorite mathematical object. Let's just call that star, some class of objects, and we're going to find a moduli space of star, or simply a space M, such that the points of M are in bijective correspondence with isomorphism classes of that object. So for instance, you could take star to be smooth, connected projective curves of a fixed genus. And then you get MG, which is the moduli space of smooth curves. This is our primary example in this course. But there's a lot of variance on this moduli space. Rather than studying abstract curves, you can study curves embedded into the plane. So let's consider the moduli of degree D plane curves. And we're going to say that two plane curves are equivalent if they're projectively equivalent. What that means is that there's an isomorphism of projective space sending one curve to the other. So in other words, you can think of this moduli space as a space of degree D homogeneous polynomials in three variables up to scaling. So the projective space of functions of P2 of sections of OD. But mod projective equivalence, that is automorphisms of P2, PGL3. So this is just another example. And I wanted to highlight here that there's that when you define a moduli space, you don't only need to specify what the objects that you want to parameterize are. You need to say when two different objects are declared equivalent. And so, specifying a moduli space is both specifying the objects and specifying when two objects are equivalent. And so there's even in this case, there's other equivalence relations you might consider. For instance, you can consider abstract isomorphism. And then this space would be sort of the locus of, this would then be like the moduli would be a subset of MG consisting of those that happen to be embedded in the plane. Or you can say that C is equivalent to C prime if C and C prime are equal as subschemes of P2. And then then this would be the parameter space of just homogeneous polynomials of degree D in three variables up to scaling. And another variant, so you can consider, curve, it's a very useful way to study smooth curves is to embed them into projective space. You can embed them into P2, or you can use this fact that any smooth curve is embeddable into P3. But you can also, relax this condition and consider maps to projective space that aren't defined by very ample line bundles, but only by ample line bundles. And maybe the most interesting and important case of that is when you consider maps from smooth curves to P1. So these are branched covers of P1, and say degree D. And so what these look like is, you might have, here's P1, and it might look like a cover like this, where there's branch points, and then at these branch points, if you zoom in locally, this map looks like z goes to z squared. And so you can consider the moduli space of branch covers. This is what I've defined here. It's the Hurwitz moduli space. And you consider degree D maps to P1, where the source is a smooth connected projective curve of genus G. And here, maybe to be precise, that we say that that two branch covers are equivalent if there's an isomorphism over P1. And maybe moving on to example 4, this is a very different flavor of a moduli space, but equally important. And here we're gonna fix a smooth projective curve C, and then we're gonna try to parameterize all vector bundles of fixed rank and fixed degree on C. So this is MCRD, moduli of vector bundles of rank R and degree D. You might ask, why am I fixing the rank and why am I fixing the degree? You don't have to. Just like with MG, I didn't need to fix the genus. But if you want to have any hope of getting a finite type variety, whose points are in bijective correspondence, then you need to fix these invariants. Otherwise, the moduli, like the moduli of all curves will be the disjoint union over all G of MG. So we fix these invariants to have some hope that it's a variety. And this example, we won't spend too much time on it in this course, but we will visit it frequently. This is a very important object in algebraic geometry and has a lot of interesting generalizations, right? You can consider the moduli space of sheaves on surfaces or other higher dimensional varieties, or the moduli of complexes, and then you get into Bridgeland stability. But I think if you're interested in any of those spaces, having a solid understanding of this one, vector bundles on a curve, is a good starting point. And yeah, maybe I should say, so far, I'm being kind of vague here, and I'm defining everything as sets. This is really silly because, after all, any two complex varieties have the same cardinality. Namely, their complex points are in bijection. But so in order to make this more interesting, we would like to endow these spaces with more structure. Structure of a topological space. Might add a sheaf of rings. In the end, we want these to be algebraic varieties, and this is what I call the moduli miracle here. Is that for these spaces I've defined, these actually have the structure of algebraic varieties. Perhaps more generally, like if you're interested in moduli spaces in other contexts, in the analytic category, or the complex or topological, you would sort of hope that the moduli space has the same structure in some sense as the objects you're parameterizing. Any questions? All right, so I'd like to give a historical perspective on MG before we start introducing the technology of stacks. Let's discuss the history, and the story really starts with Riemann in 1857, or actually, like he declared that, or he said that the number of moduli, whatever that means, of smooth curves of genus G is 3G minus 3. He in fact gave several different heuristical arguments for it in the 1850s and 60s, and I'd like to just give try to present one of his arguments. And the idea is to compare MG to the Hurwitz moduli space. Namely, I have this diagram here, and remember that an element of the Hurwitz space is this branch cover, And so there's a map of moduli space from the Hurwitz one to MG where you just forget the morphism to P1. You just remember the curve. And likewise, any curve, any branch cover, is branched over certain points. So you can just map to the unordered collection of branch points. And if you compute using Riemann-Hurwitz, it will tell you how many branch points there are in P1. Riemann-Hurwitz, the statement is that whenever you have this finite morphism of smooth curves, that if you take 2 times the genus of the source curve minus 2, that should be equal to d, the degree, times 2 times the genus of the image minus 2, plus the ramification divisor. And the number of branch points is the degree of the ramification divisor, r, and just by this formula, you get that it's 2d plus 2g minus 2. So we have this Hurwitz moduli space, and we have 2 maps to these 2 other moduli spaces, right? And we're mapping to the symmetric product here because it's an unordered collection of points. And so, yeah, what we see is clearly this space, we know that that this map here, what you can show is that this map here has dense image. In other words, if you give me a general collection of 2d plus 2g minus 2 points, as long as you choose d sufficiently large, there is a branch cover over it. And in fact, it is only finitely many. So this map has finite fibers. So one way to think about that is that if you think about a branch cover, away from the branch points, this is a covering space. So it's locally just like a trivial d-sheeted cover of some open in P1. At the branch points, it looks like z goes to z squared. And so you can think about like globally, a branch cover is just gluing these trivial covers along permutations of SD. And so there's only a finite number of data that determines how you glue these trivial covers to get a globally branch cover. But generally what this argument then says is that, therefore we know that the dimension of the Hurwitz moduli space is the same as 2d plus 2g minus 2. And so the way Riemann got this calculation is by computing the dimension of the Hurwitz moduli space in 2 different ways. So we can also take the fiber of this morphism over a curve C. And let's just declare that the fiber is Hurwitz covers a degree d of a fixed curve C. So this is the moduli of C to P1 with C fixed. And so we can compute the dimension of the space here as just the sum of the dimension of MG plus the dimension of the fiber. And of course, this is what we want to compute. And this one we don't know yet. So the way we're going to get at the dimension of MG is to compute the locus of the dimension of the degree d covers of P1 by C. So yeah, to compute this, let's fix C now. So we fixed a curve, and now a degree d map to P1 on C, is just defined by a line bundle of degree d together with 2 sections mod scaling. And so this line bundle you can think of as an element of pic d of C. And you may know that pic d is the same as pic 0, which is the Picard. You may know that that's dimension G. But you can also get at this more explicitly. Like you could think of, rather than thinking of a line bundle of degree d, you could think of effective divisors of degree d. So you could take like just d points on C. That gives you an effective divisor, and that defines a line bundle. But the data of this is, whoops, I have the eraser on. The data of this then is a line bundle plus a section up to scaling. And if you think about what a section up to scaling is, that's H0 of L minus 1. And you can compute that by Riemann-Roch as just D minus G. And so you can see, you can realize, if you realize pick D as like the quotient of effective divisors, then what this says is that the relative dimension of this map is D minus G. Since this has dimension D, then we see that the Picard, the parameter count gives you a dimension G for the choice of line bundle. And then 2 sections modular scaling, that's 2 H0L minus 1, and that's equal to 2, again by Riemann-Roch, 2 times T plus 1 minus G minus 1. And so altogether, if you add these 2 numbers, G plus this, hopefully it's 2D minus G plus 1. So that tells us what this is, and then subtracting, if you subtract 2D minus G plus 1 from 2D plus 2G minus 2, you should arrive at 3G minus 3. So that's one way to give a heuristic argument for that. And sort of an interesting argument, and it uses the Hurwitz moduli space, and that which will frequently show up in this course as well. Maybe most notably in the argument for the irreducibility of MG. I should also say that we'll revisit this calculation later. We're going to give, using the language of stacks, we'll define dimension, and then we'll show that the dimension of the Dewey-Mumford stack of smooth curves is also 3G minus 3. So that's some 19th century history. And, Riemann never showed that it was a complex manifold. Complex manifolds weren't even introduced until the 1940s. Riemann called it Mannigfaltigkeiten, which means the German word meaning like manifold-like. And so, I mean, at this point in the 1950s, there are already topological and analytic viewpoints of this theory, but algebraically, it was they in 1958 who said, as for MG, there's virtually no doubt that it could be provided with the structure of an algebraic variety. And Grothendieck tried to do this. He was aware that the functor of smooth curves is not representable. And so Grothendieck in 1960, aware that MG was not representable, he considered, rather than parameterizing smooth curves, you could parameterize smooth curves with level n structure, that is a curve together with the basis of homology. And then he showed that was representable. But even with this space, he struggled. I mean, if it's fair to say Grothendieck struggled with anything, he was unable to show projectivity of that moduli space. And it was only a few years later that Mumford came around and proved that MG is a variety. And
can I ask a question?
Oh, sure.
Yeah, why did Way think it should be an algebraic variety? Like, what was his reason for thinking this, or is he so sure that MG should be an algebraic variety?
Sorry?
Why was Way so sure that MG should be an algebraic variety?
Good question. Yeah, I don't know. I mean, maybe you can write down local coordinates or not. Yeah, I don't know why he thought that.
Okay.
I mean, yeah, it's a good question.
Did they know that the moduli space of abelian varieties was already an algebraic space by that point?
That was around the same time they were. I think that, yeah, I think that the moduli abelian varieties was done just before that, right? And in fact, Mumford's first proof, you relied on the moduli abelian varieties.
I see.
And so Mumford did show that MG is a variety, and he used geometric invariant theory, and this is ultimately, what he was awarded the Fields Medal for. So Mumford used the theory of geometric invariant theory, and very quickly, I mean, the idea is very basic, and it's, rather than parameterizing just smooth curves, you add some additional data. Maybe it's a basis of H1, maybe it's the data of a fixed embedding into a given projective space. And then you try to mod out by that choice of data. You show that with the additional data, it's representable, and then you try to quotient out by the group of equivalences. And so GIT was highly successful in constructing MG together with a number, with many other moduli spaces. And I should say that, there's many other approaches to constructing MG. There's analytic and topological ways of using type Mueller space. But our approach will be entirely algebraic. And we'll sort of synthesize the ideas of GIT, but using stack theoretic arguments. And almost everything I say in the entire course has parallels in the analytic or topological categories, but the methods and the way you prove things are so different. But conceptually at a high level, there are a lot of parallels. So the way we're going to try to show this, the main goal, which is to show that in the end, MG is a projective variety, is this three-step process where we first show it's a nice, like, smooth proper de Lee-Mumford stack, and then we'll use a theorem of Keelan-Morey to show that there's a coarse moduli space. All of this will be defined later, where we've gone from like the calligraphic font to the Roman font, where this is going to be at first just a proper algebraic space. And then finally, using Kolar's results, will show that like a certain tautological line bundle on MG bar descends to something ample, and therefore proving MG bar is projective. All right, that's the whole goal for the course. But it's going to take us some time to get there. Any questions on this historical account?
Maybe quite a stupid question. Maybe could you fix the meaning of varieties? I mean, there are many conventions. So.
Well, I'm being vague here. I'm being vague enough that I don't think it matters. I mean, I'm going to be using scheme theory. Like when I define things precisely, I'll be using the language of schemes, and I'll be very clear when I assume something is irreducible or finite type or whatnot.
Okay. I mean, if you assume this variety is separated or geometrically integral or something like this.
Which one? Which variety?
I mean, the variety in general. Like you say, you show
I don't
that
think I'm going to be
MG is a
using the
variety.
word variety. I'll use scheme. Is that? Yeah.
Yeah. Okay.
But yeah, I mean, okay. If I say variety, I mean, what do I mean? Yeah, a reduced scheme of finite type over a fixed field.
Okay. Thanks.
How different is this approach from Mumford's original one?
Well, I would say it's a different approach. I mean, many of the ideas, but there's a lot of intersection in ideas. I mean, the proof of MG bar, using geometric invariant theory, essentially what you show is that any smooth projective connected curve can be embedded into using like the tricanonical, the third power of the sheaf of differentials, into projective space. And then you use growth and Deeks theory, the Hilbert scheme, to parameterize closed subschemes of a given projective space with the right Hilbert polynomial. And then you realize that the way you went from your curve to the embedding is you chose a basis of the sections of this third power of the canonical bundle. And so then you try to take the corresponding Hilbert scheme and then mod out by automorphisms of projective space. And the real challenge here, it's a beautiful theory, and the real challenge of this is that at some point you need to identify the GIT semi-stable curves with the geometric stable curves, and that's the most difficult part of that. But in the end, it's sort of miraculous that the machinery of GIT handles all 3 steps at the same time. You get projectivity for free, and if you can really understand the Hilbert-Mumford criterion, you can actually it tells you what additional stuff to parameterize at the boundary in order to compactify your space. But there's a lot of ideas at GIT that we will use.
Okay, thank you.
Great. Since I have time, I wanted to just jump into one of the subjects that one of the new abstractions that you really need to accept when you want to learn the theory of stacks and moduli, and that is like the functorial worldview, and that is, in other words, Grothendieck's worldview, where you view spaces as functors. And maybe to set this up, basically, this idea is that instead of studying like a variety or scheme or topological space X, you study it by pegging it with maps from other objects. So the way you understand space X is by considering all maps into it from other spaces. And so like in the category of schemes, so here throughout this course, we'll use this notation for the category of schemes. And we're interested in contravariant functors, F, from the category of schemes to sets. And maybe the first example of a contravariant functor is a representable functor. So if X is a scheme, we'll let HX be its functor of points. So this is the functor that assigns a scheme S to the set of morphisms from S into X. And basically the main idea here is that the functor determines X. HX determines X. So one way to think of that is that, if you evaluate HX at a field, you get the K points of X. So you might think that you can get, like, as a set, you can recover X as the union of all fields as you vary over different fields. But if you want to get the generic points, you have to allow maybe arbitrary extensions. And then you want to mod out by an equivalence to say that, 2 field value points are the same if there's actually a third field that's larger than these 2, which are such that the points agree. And so so once you have a functor, the way you get its set of points is just to evaluate it at points. But then you can also try to build a topology and build a sheaf of rings on it to reconstruct it as a scheme. But in the end, this is all formally disguised as a completely formal argument called Udeda's lemma. And this is sort of Grothendieck's. It's not hard to show, but it's incredibly powerful point of view when studying moduli. And the Udeda's lemma is the assertion that the functor determines X. But maybe more precisely, it says that if you have any other contravariant functor, G, that morphisms between the functors is bijective to evaluating the functor. And so here in this map, if I have a morphism of functors, say that by which I mean a natural transformation, then this, if I evaluate, for any scheme, I get an induced map of sets, but in particular, I can evaluate this functor at X, and then I could take the image of the identity map from X to X. And so this gives me an element of G of X. And this is the way the bijection is determined. So yeah, I think there's a point, like, at least I remember this in second year of graduate school, where I started absorbing this functorial perspective, and it really changed my worldview of mathematics, where you start thinking of every space as a functor. You think of the affine line A1. What is a map from a scheme for the affine line? It's just a global function. Or projective space. Projective space represents a very natural functor. This is in Hartshorne, where a map from a scheme S to projective space is determined by this data, a line bundle, and n+1 sections that globally generate L. And so there's a bijection between maps from the scheme S to Pn and this data. And maybe in other words, like if this condition that SI that the sections generate L, this is equivalent to what this means is that there's a surjection that if I just take these n+1 sections and map to L, that this is surjective. So in other words, projective space is representable by the functor, which parameterizes quotients of the trivial bundle of rank n+1, where the line bundle quotients of the trivial vector bundle. And taking this perspective is a clear way to generalize this to other rank quotients, and we get the notion of the Grassmannian. So you can define the Grassmannian as a functor. The Grassmannian functor is the functor from schemes to sets, which takes a scheme S to the quotients of the trivial rank n vector bundle to rank k vector bundle quotients of it. And the fact is that this functor is representable by a scheme, and then we're going to use the same notation. In fact, maybe this is a warning here, is that we'll always conflate like a scheme X with its functor points Hx. And so and so this functor is represented by a projective scheme over spec Z. And then even going further, you can generalize this, and you can get quote schemes and Hilbert schemes this way, which we'll address later. Maybe as a fourth example, let's rather than considering functors from the category of schemes, let's consider functors from the category of affine schemes. This is affine schemes, and in order to absorb this functorial perspective, I recommend this following exercise that to define a scheme, it's equivalent to define a scheme is equivalent defined as a functor from affine schemes to sets, such that it's locally an affine scheme. Okay, and that takes some work to make precise. And to make it precise, we say that there exists open subfunctors Fi and F, such that the following two properties hold. First, that each Fi needs to be representable by an affine scheme. And then the second is that it has to cover F. And so let me quickly say what that means, because we'll use, this uses many concepts that we'll develop further later. And first of all, okay, subfunctors is okay, but we need to specify what it means for a map of functors to be representable by open emergence, or what it means to take an open subfunctor. And so here, we say that Fi and F is open if for any map from a scheme S into F, you compute this fiber product. So you have Fi to F and S goes to F. You compute this fiber product. This is the fiber product in the category of functors. And note that here I am already abusing this notation right here, because like F is a functor, S is a scheme. So what I really mean here is this really means a natural transformation from HS into F. But I prefer to abuse notation. So we need to know what the fiber product is in the category of functors. But actually, this is a lot easier than learning about the fiber product in the category of schemes. Like, namely, like if I wanted to know what fi cross f is as evaluated at a different scheme T, this is just the set theoretic fiber product of evaluating everything. Maps from T into S. And so this is the set fiber product. And actually, if you think about how you show the existence of fiber products of schemes, you're essentially using the same machinery. You define, I mean, the universal property of the fiber products is that a map from like a scheme T into the fiber product should correspond to maps to the two objects that agree under composition. And basically what you're defining is the functor that the fiber product should represent. And then the argument to show it's representable is just this local argument of the same, essentially using this exercise. Basically, like reducing it to affine schemes where the fiber product is just given by tensor product of the rings. And finally, now that the map from Fi to F is representable by open immersions, we can define any other property we want. So, for instance, we define to say that the map is surjective means that for any map from a scheme S, this induced map of schemes is surjective.
I have a question here.
Mhm.
So when you say these definitions, are you assuming Fi times S over F is representable by a scheme?
Yes. Okay, yes. I think I didn't say that. That's a good question. Yeah. So, right. Okay. So going back here, now that we've addressed fiber products of functors, when we define open subfunctors, what the condition is for every map from S into F, if I take this fiber product, that this map here is an open immersion of schemes. So in particular, this fiber product is representable by a scheme, which is an open subscheme of S. Yeah. Thank you.
Sorry, I'm confused about why this wouldn't be circular. Because it seems like you're trying to define scheme, but you're using the concept of scheme to define it.
Yeah, well, I'm using the concept of affine scheme to define it.
So are all the schemes on the bottom affine?
No, I mean, I think you raise a good point. I guess you raise a good point that you need to really specify. I am using the language. I'm using the language of open immersion. So, yeah.
Although it sounds like you already are happy with, I mean, you could just work in I think everything can be done in affine schemes. Then everything you said still makes sense, and then you're defining scheme.
Yeah.
So isn't there a problem with Fi cross S being affine? Because not true that every sub-scheme is going to be affine of an affine.
I think you would need to define a scheme, affine scheme, and an open, what it means to be, what an open subscheme of affine scheme is. But since we all know scheme theory, and since we're building on scheme theory, why not just take to check that you could interpret this exercise as to interpret that a functor is representable by a scheme is that you have to check these conditions. But yeah, you can also rework this to precisely to define a scheme with only building on foundations.
So
yeah.
In the case that we're doing,
is there another comment? Okay. Right, and actually, this perspective is so useful, and like this is essentially how we're going to define these critical notions of algebraic spaces and stacks later.
Sorry, so I don't want to keep bringing it back to this point, but
from my understanding, Fi and S we've assumed to already be representable by schemes, correct? In that diagram that you've drawn.
Wait, which one?
In the diagram that you've drawn for the open immersion of schemes, Fi and S are already representable by affine schemes, right?
Wait, affine S.
Or I guess S isn't affine, but S is representable by a scheme.
Maybe
Yeah,
we could take this to the end and for longer discussion.
Yeah. Yeah, I'm not sure I got. Yeah, but just, quickly, what's your question?
What I was just wondering is the fact that are we assuming that Fi times like the fiber product of Fi and S is representable by a scheme in the notion of open subfunctor, or is it just a result that when we take the fiber product of representable schemes, it will always be representable?
No, here we're defining what it means for this for this to be represented by open immersions. So yeah, so the condition is that this functor, the fiber product defined as a functor, that this is representable by a subscheme, an open subscheme of S.
Okay.
Yeah. And there's still, yeah, okay. Right, and so yeah, but this perspective of schemes is how we're going to view algebraic spaces and stacks. So maybe as like a broad overview, let me give a sort of a chart of these objects that were introduced in this course. And so, you know, we're going to view schemes in algebraic spaces as sheaves, where, you know, by a sheaf, I mean a contravariant functor, say from the category of affine schemes or the category of schemes, your choice, to sets, and then I need some sheaf axiom. Something that looks like, you know, if I have a cover UI of a scheme U, then, you know, F of U should map to FUI, which should map to the product. And that you require this to be sort of the equalizer, to be exact. And so that the underlying, so what an algebraic space then is just, whoops. So, sorry. Still learning how to use Notability. So yeah, algebraic spaces will then be sheaves, but rather than saying, like if schemes are Zariski locally affine schemes, then an algebraic space will be a tau locally an affine scheme. But then going further, when we define Deligne-Moffat stacks and algebraic stacks, we need to then, you know, include automorphisms and isomorphisms into our category, and then to develop the concept of a stack. But in the same way, you know, a Deligne-Moffat stack will just be is a tau locally affine, while an arbitrary algebraic stack is smooth locally affine. And we'll get there later. And maybe give one more example, returning back to MG, of how could you possibly view MG as a functor? And so let's define the functor of MG being FMG, where to the scheme S.
Can I ask a question about the previous slide?
Sure.
So in the previous slide, so where do the automorphisms come from in the stacks picture if you're just gluing schemes?
Yeah, yeah, that's a good question. Well, like yeah, I mean, it's encoded into the definition of a stack. So you can think of, you know, sort of a stack vaguely as a contravariant functor rather than just sets. You can map to groupoids. So rather than parameterizing objects over a scheme S as a set, you think of you define it as a groupoid, and then you have to show all these notions of a tau local or smooth local. You have to formally define them in this context, which we will do, but yeah, it's not easy.
Okay, thanks.
Right. So yeah. So you can define this functor MG, and you can hope that it's representable. But the unfortunate reality is that it's not representable. And the main reason is automorphisms. But let me just give, say, a general principle of why many functors are not representable. So let's just consider, you know, a functor f, and now let's work with schemes over the complex numbers just for simplicity. And let's suppose that we have an object E over some variety, some C variety S. So this, you can think of this as a family of objects parameterized by this base scheme S. And so if you fix a point in that scheme, you have then an object over C. Namely, right, this is just coming from the restriction, you know, it's a functor after all, so you can restrict along morphisms. So if you just restrict along the inclusion, you can pull back your object E to get something with values in f of C. And let's suppose that we now have constructed this family of objects satisfying these two properties. One is that all fibers are isomorphic, and that two, globally, it's not trivial. Meaning it's not the pullback of an object over from spec C. Then I claim that f is not representable by a scheme. And the reason for this is, I mean, well, let's suppose that there is a scheme X representing f, then all of these objects ES, they're all isomorphic, so they define one point, single point X. And so what we get is two maps two maps of schemes from S to X. One map here being defined by the object E. This is because it's representable, the object E defines a map from S to X. And on the other hand, there's this constant map, that is the map that factors through spec C via this inclusion of the point. And these as a map of schemes, since S is a variety, it's reduced, and both these maps, you know, are constant, they're the same map. And so that shows you that E itself must be trivial, which contradicts our hypothesis. And now, what I would like to highlight here is that the presence of automorphisms in your moduli allows you to easily construct non-trivial families where all fibers are isomorphic. And let me just give you one example without the details of how you might do this in algebraic geometry. Like in topology, for instance, you could just like take your circle, take the trivial object, and then just glue along with an automorphism to get a non-trivial family over a disk. We'll do a similar thing, but using the nodal cubic. And so here we have P1. So in this picture, in this bottom here, this is P1. This is the nodal cubic obtained by gluing these 2 points, 0 and infinity. And here we over P1 we have the trivial family, and then if we take a non-trivial automorphism, you know, like just like the nodal cubic is obtained, the nodal cubic here is obtained by gluing P1 along these 2 points. If I take the trivial family and glue these, like every fiber here is isomorphic to C. So if I glue these two curves here along this isomorphism alpha, I get a non-trivial family. Well, I should have really drawn this more of like a Mobius band, but my artistic skills are lacking. But you can show that you can do this in a way that you can get a non-trivial family with all the fibers are isomorphic. But the general principle I want to share here is more this high-level picture, is that the presence of automorphisms obstructs representability of the functors. And this is why we introduced the language of stacks, because, you know, we really care about functors being representable. One reason is that it gives you universal families, for the existence of universal families for free, and this is why we introduce stacks. Maybe I should sort of summarize this introduction by this trichotomy of moduli. really, kind of corresponding to properties of the automorphism groups. There's really three cases what happens depending on whether the automorphisms are whether there's no automorphisms or only finite automorphisms or infinite automorphisms, right? If there's no automorphisms, then often, then you at least have a hope that your functor will be representable. And if it is, it's going to be an algebraic variety or maybe an algebraic space. And right, the defining property was it's Zariski locally or a tau locally in affine scheme. Meanwhile, with the Lean-Mumford stacks, this corresponds to moduli of finite automorphisms, and these will be a tau locally in affine scheme. And the case where you have infinite automorphisms, we already saw this with the case of vector bundles of fixed rank and degree. All of those that have infinite automorphisms because there's always the C star automorphism of sheaves. And we land in the category of algebraic stacks. And so and so in this trichotomy, let's see, like we've already discussed some of these examples here. The projective space, this is the Grassmannian, there's a Hilbert space, this is quote space. I mean, you can also think of M0n. Finite automorphisms is MG bar, moduli of stable maps, and then for infinite automorphisms, you have moduli of vector bundles or sheaves or complexes. And an important example of stacks that appear is things that are quotients, and we'll introduce quotient stacks later.
Jarod, can I ask a question about where an example fits into this trichotomy?
Sure.
So one of the things I like is to think about you take a fundamental group of a surface. And when I say surface, I mean a real two-dimensional thing. So what you guys would call a curve. And then you look at representations in the, let's say, a semi-simple Lie group, modulo conjugation in the Lie group. So Hom pi G mod G, which parametrizes flat connections on on principal G bundles on the curve. So would that fall into this third example because it is parameterizing some kind of vector bundle but with some extra structure? Or
yeah, I think so.
Okay, thank you.
I think so. That's like it's sort of, yeah.
I mean, I know these are defined using GIT quotients. I mean, if you want to be careful to define them, you have to define them using GIT quotients, and then of course there's different components to these things. But it feels like it should be in the third piece here. Yeah,
that's right. Yeah, like the moduli of vector bundles and the moduli of G torsors, yeah, they fall in that category as long as your group is positive dimensional.
Okay.
Right, and even as Jarod was pointing out there, a lot of times moduli spaces are constructed as quotients, and a very important example of that is these quotient stacks. And the way they fit into this trichotomy is that if you have, this action, you have this action G on X, and if the action is free, in other words, that the induced action map is a monomorphism, then you land in this first setting where you have no automorphisms. But you can also have finite stabilizers. But in general, if you have any action, as long as it's in like an algebraic group acting on a scheme, then it will be represented by an algebraic stack. But ultimately what we want, I mean, we are interested in stacks, but ultimately we would like a moduli variety, because then we can, work with it as we work with other projective varieties. We have Hodge theory and all the tools of projective geometry at our disposal. And so if you're in this first setting with no automorphisms, I mean, then you're already good, basically. You already have an algebraic variety or space, and maybe you hope to prove it's projective. But in the case of MG or MG bar, what you need to do is construct a coarse moduli space that basically removes the automorphisms. You lose the universal property, but you sort of like, there's this balance. You trade off the universal curve for actually getting a variety. And then in this final category, which we won't discuss that much yet in this course, is that you can do a similar thing, but you use the notion of a good moduli space instead. But yeah, that's my broad overview. I think that's basically everything